Recording in progress.
All right, so we're going to be talking about static memory today, and this is just kind of layering on a little more understanding about how C++ manages memory, and also giving us a couple more useful tools that we can use in our classes and our functions. And we'll also take an opportunity to introduce chess, which is kind of our last very big homework. So that one is one that everybody will want to jump into as soon as they wrap up 6. So hopefully everybody's finishing their homework 6 shared pointer program. We got a quiz 6 too, I know, so it's kind of a lot of stuff. We've got 2 labs this week. The lab tonight is pretty straightforward. It's just getting used to some new syntax. So it's really mostly about just sort of picking up a few new tricks from the lesson today. And then we will move into class hierarchies or inheritance. So we haven't talked yet about how we might stack or inherit from higher level classes, but that's a whole thing that C++ offers. And when people talk about polymorphism in object-oriented coding, that's a really big word that gets thrown around. Usually they're thinking about some of the features that we pick up by having inherited classes. So that'll be a new big topic, and that'll really be important in our chess. So we'll just touch on that briefly today to introduce what we're trying to do, but we'll definitely need to dig into class hierarchy to give you all the tools you need to sort of understand and finish your homework 7, okay? And so that's sort of 2 weeks out, starting our clock today. So now there are 9 homeworks listed, I think, including the one with the potions homework. I think that's still out there. So essentially, I will drop 2 of your lowest homework. So just reminding you of that so you don't feel like, oh my gosh, we got to do another homework I didn't plan on. So if you got, 7 good homework grades, you're going to be good. Just figure out which ones. And 9 is always out there. If you blow up on 2 and you got to like hurry up and race to the finish to get 9 in, at least you got another option for another homework out there. So keep that in mind. For today, we're going to introduce chess, but predominantly we're going to talk about static variables and static members and static methods, which is a little mysterious, but once you understand it, it's actually really, really useful. And you start seeing it everywhere once you know what's going on. Basically, static variables are things that stick around for a really long time, usually until the program terminates, or if they're inside of a class, they stick around as long as an instance or the class, or not as instance, as long as the class sticks around, which usually is going to be as long as the program is around. So we'll look at all these different ways we can use this special qualifier and its effect on the different kinds of things that we've used before. And then we'll just kind of dive into our chess. So not a really huge lecture. Maybe some key things to remember. So this is from our last lecture and will definitely help you to get that last, correct answer out of your homework 6. So remember that when we have a weak pointer, it is possible that one of our friends might have been deleted. So the weak pointer doesn't go away, it's still there. So what we really should be doing correctly in order to stay out of trouble is making sure, first off, that the use count of a particular, let me get rid of this. Sorry, Esley, I cannot let you in. Is Esley in the class today? Yeah, sorry, I can't let folks do that. Most of you know. So if the use count of that particular pointer is greater than 0, actually, and that is a little bit of a typo, in fact. So it really should be if the count of a friend that we put in there is greater than 0, and if it's not expired, right? So if the shared pointer is not expired, then we actually want to follow it and get a lock on it, okay? So if it is expired, then don't follow that pointer because you're going to either get some corrupted data or you might actually crash. So do keep that in mind. That's a very handy method that we may want to use to check those weak pointers, okay? And remember that we grab a lock to basically create a shared shared pointer to access that friend's name. If it's expired, then we don't want to do that because that means that person has already been deleted and they're no longer in the database. Okay. So that's something to just keep in mind. If you get confused on that, just let me know and keep a kind of a mental note that that's probably where things are going to go off the tracks a little bit. Okay. So that's for homework 6. Now, just looking back a little bit, stuff we talked about when we talked about pointers and dynamic memory management, we said that ironically, the area we call text memory is all about what's not text, right? It's really about zeros and ones that represent our executable code. So when we compile our program, our C++ program, we're making it into zeros and ones for this specific processor on this specific computer you're using. Or in the case of Replit or Program IZ, it's being compiled into zeros and ones for the server that's somewhere off in the cloud. It could be an Intel server, it could be an ARM server, it could be something else entirely. But that's what we call the text memory. The stack is where we have variable names. I usually color those in blue. This is stuff we've mentioned a few times about creating stuff on the heap using new and potentially kind of filling up memory and swapping, which slows everybody's computers down very often. And then some special areas for weird little animals like const char string, hello world. That kind of a variable can never be changed. It's kind of a read-only thing, okay? So, but this one area over here is for uninitialized variables. So these are often like global variables or static variables. And those are the ones that we're going to look at today. Even though they might live kind of somewhere in our code, like inside of a function or inside of a class, they all sort of get shoved over into this special area of memory. So this is really kind of how C++ does its thing. And other languages kind of manage that stuff a little bit differently than C++ does. So now, this is just a little interesting side story. I found this last year. It really kind of blew my mind. Everybody's probably heard about the Voyager satellite, right? And all of its incredible adventures. So you may have missed this thing where it actually just went silent and then started burping back junk responses. This was about almost a year and a half, 2 years ago, and they did not know what to do. It's about 44 minutes to send a command to the Voyager and then to hear back, did I do it or did I not? And so they weren't getting any kind of positive support, just junk garbage stuff. And after 5 months, they really were not able to really accomplish anything. So they basically started looking at this text area of memory and assuming that, well, maybe this got some bad chunks of memory. Maybe there's parts of the executable code that's just basically blown up because of, radiation and whatnot. The memory in that part of the computer is bad. So they started sending commands to redistribute the text area to different areas of memory to route around where they think they had some problems. So really low level stuff, essentially just piecing together good pieces of memory, and they got this sucker rebooted again, which is really pretty phenomenal. Like it just kind of came back to life. So it's back and it's communicating still. It can't do much because the batteries are pretty low, but it was quite an impressive piece of coding that the folks were doing there. And it really was right around this area of text memory, right? How do we actually find enough space to store that whole thing in there? So traditionally we call those things sort of the stack or automatic area of memory, as we mentioned before, dynamic, where we put stuff on the heap using new and delete, and including shared pointers that, or make shared, right, that create these new instances. Those are on the heap as well. And then today, again, is this static section. So we'll talk about that in detail right now, pretty much. Just a reminder, though, as we kind of march forward, we did introduce this interesting thing called a mutable variable. So when we have a const method that is not allowed to change anything except for one of the things is mutable. So remember that as we kind of play around with stuff over the next couple of weeks, these const methods, which are marked const because the const is over here, not over here, right? That means, hey, this thing can't change anything except for the mutable variable there. Okay. So set me can do that change, and even a constant instance of a class can actually call these const methods, right? Because even though they're changing something, it's allowed under that const rule. Okay, so just a little bit of stuff on the side. So we're going to add to that today with this static data type. So static data types can apply, or the static qualifier can apply to any variable or any method, and they kind of exist at file scope. So we create something inside of one file, and we don't really have duplicates of that anywhere else. So think of it kind of like a global variable that doesn't go away. And so we can apply it to variables in main. They just sort of stick around for a really long time. We are going to see we can also apply it to members of our class, our data members, or our methods in our class. And we can even actually apply it to variables inside of functions, which is kind of an interesting trick I'll start out by showing you here today. Okay. So there's a couple corner cases there, but let's sort of take a look at the areas in which we would kind of use them for something helpful. As we all know, functions actually don't have any memory, not really, right? So usually whatever happens in a function, it all goes away when the function is done. The function returns some value and the function's role is over. And underneath everything, it's really getting popped off the memory stack. That's why we kind of call it automatic. So even functions kind of go on a stack and get popped off, unless we declare that they have a variable that we don't want to go away. So it turns out that a static variable in a function is almost like a data member in the instance of a class. We never want to try to muck around with it by taking a pointer to it or anything, but the function can actually keep some memory so that it can do some interesting things. Okay. So we are not creating const static variables in this particular case, but we can apply the static to any one of these things. And we'll start out by doing that inside of a function. Okay. So here's an example of what I mean. If I say f1 is a function and I put a variable in there and set it to 0, every time we call that function, that thing is going to get set to 0 as the very first thing. And then if we print that out, it's going to, of course, say 0. And if I increment it, it's still going to say 0 every time we call the function, no matter what. Okay. So that A gets incremented, but then it goes away and gets reinitialized. So that's a pretty typical situation. Okay. But if we put the static in front of there, it's this weird new kind of animal that remembers its initial value. So in this particular case, it's going to initialize that the first time we call the function. And then from then on, the B is going to get incremented. So this is a private variable that's locked away inside of this function, but we can kind of have a little piece of memory, right? So let's take a look at this example here. We can just kind of jump into this code real quick and refresh. There we go. Let me zoom up on that a little bit. Okay. So here's my function f1, right? Normal variable, right? Even though I increment that variable inside of the f1 function, we're not going to see that thing increase. Now here we have two of these. This is inside of the function inside of its own scope, right? So it's really pointless to kind of have this. We can't really reach inside and use it, but it's just showing you that you can create that in that scope if you want to, okay? But this is the one here that'll be interesting. This one is going to start out as 1, and then we're going to print it and increment it. So every time we call our function, we should see that it increments that variable, okay? So this is our global variable that's going to stick around forever. That's a little bit different than what we're doing down here. And here's another example of a static variable, but this is really what we're after here. F1 is never going to increment that local variable, or it's going to reset it every time. F2 will not, right? So we call the function 3 times. Our count that's getting printed out is never going to increment. Okay, so I know we have a lot going on in here, but this is going to be 0 incremented, then 0 again, etc. Down here, this one's going to start out as 1, and we do see it slowly climb up. Okay. So it is a little bit like a private data member in a sense, right? So let's see if we can kind of put this to some good use. So we want to create a function called buy widgets, and we'd like to have it have a little bit of memory about its initial inventory, okay? So for this particular function, we're just going to sort of give it a fixed inventory of 100 to start. But we could have just as easily passed that in to some argument, right? And had that value here. That's going to happen one time, right? But we're going to leave that out for now. Okay. So we're going to start out with 100 widgets, right? We want that to be static. Okay. And now every time we, sell some stuff, we can just check to see our data member there. We have this many widgets left. If what you want is less than what we have, then we'll go ahead and update the widgets, right? And then print out the answer for that. So let's just try this real quick. We want to buy 10 widgets. We had 100. Now we only have 90. Now we call the function again. We'll buy 5, right? Oops, try that. Buy 5. Uh-oh, did I crash my program? Maybe I gave it some bad data. Let me start that again. Sometimes. Okay, I'm gonna buy 10. We have, I bought 0. Now they're only, let's try that again. There we go. Now I bought 10. Yeah, I don't know why my cursor is not doing the right thing. I'll buy 5 this time. There we go. Now we got 85. So pretty straightforward, right? We just have now the ability to have persistent variables inside of functions. So you can imagine maybe a few things you might want to do with that. Keep a random secret password inside of a function that no one, including you, could ever know, right? So there's lots of ways you can lock information inside of a function so even hackers can't get inside maybe and find out what that value is. So I really like that particular application. I tend to use that from time to time just to store little secret bits of information inside of various functions that I create. Okay. And it all has to do with the static. Okay. And it initializes it the first time it gets called, one time, and every other time anything else we do is going to happen lots of times. Okay. So that's kind of our first example, but what we really want to do is explore this idea of putting static data members in a class. So this is kind of a new way of thinking about classes, but it helps to remember that classes are kind of like factories, and these factories create instances, okay? So a lot of the instances that we have created, pretty much all of them have copies of the data members inside of the instance. Static data members are kind of like chalkboards at the factory. So here we have a widget factory, and it's got a chalkboard called count. And that static data member does not get placed in the copies of the widget or the instances of the widget that the factory creates. So once I initialize the count, and it can be 0 or 10 or whatever, I can now modify that outside of those instances. Okay. So the static members hold their value regardless of whatever we might be doing in our instances. The instances can modify those static values, but they're not stored in the individual instances. So think of it like we're trying to produce a whole bunch of widgets, a million of them, right? And they happen over the course of time, and they need some place to keep track of how many widgets I've created. A static variable like this inside of the class is the perfect place to do that, okay? So let's take a look at how this might look from the outside. Here's my factory. And every widget I create is going to have an ID, but the factory is going to actually have a counter that keeps track of how many widgets we create. So if I say widget W1, I want my constructor to sort of increment the counter in the factory and say, hey, I'm widget, ID such and such. You've just created another widget. Okay. And same thing with widget 2, right? We want to increment the count at the factory. So when we speak about the ID of an instance, we usually will say the variable name dot ID, right? So W1 ID, that's getting the ID from the Brown instance there, right? But if I say W1 dot count increment, if I were to do it that way, I'm really reaching through the instance to the factory and saying, hey, I want to increment the count that's at the factory. How does it know? Well, the definition of count is that it's static. So by definition, it will not be in any of the instances, even though we're allowed to access it through the instance name. So that is admittedly a confusing feature and, kind of can certainly dupe us into thinking that it lives in the instance, but it does not. It's over there in the factory. So if I do this and I do this, now I have a count of 2 over here, right? So there's a 2 count here, right? Which would be very different if I didn't have this, then I would have a count over here and a count over here, right? But putting that static over there pulls the variable into the factory, okay? So that's really all we're doing when we use the instance as a way of getting access to it. Normally, what we do though, is we refer to the factory directly. We say, hey, widget factory, increment your count. So this to me is a more intuitive way of finding out what the count is or maybe modifying the count. And in fact, for folks who have poked around and looked at game engines or any kind of C++ large bodies of code, you start seeing this pattern. You see the name of the class followed by something like our scope resolution modifier. And then we do something with a variable. And it's like, hey, what is that thing, right? It's clearly not part of W1 or W2. And that's what we're doing. We're actually reaching back into the factory. And for various reasons, changing some value over there, okay? So data members can live in either of these 2 places, which is pretty cool, okay? Now, so here is our widget, right? So we're going to create a static counter in the factory. There's our constructor. We increment the count. That's like, hey, here we are creating another widget. So let's increment the count. And then we will just sort of talk about it, right? We'll just say, hey, I just created widget number so-and-so. And I didn't assign the ID here. So just kept it really, really simple, okay? So that's really all we have to do. But actually, take that back. The other thing we have to do, which is probably the most confusing part, is we have to initialize this value down here. It cannot be inside of here. And I'll put a little asterisk there, except for certain conditions. So we got to say int widget count equals 0, kind of like our out of class stuff that we've done before. Okay. So anytime you have a static that needs to be initialized, that's what we have to do. Okay. And notice that we're not putting the word static in it down here. We're just saying int widget :count, right? Int widget :count. Okay, question?
So I've seen const expr used in a similar way.
Yes, yes. So there are things that we can do over here that will allow us to initialize that thing in the class. So const expr is basically saying, hey, this is a constant expression at compile time, and it's okay if I initialize it now, I'll never change it again. But it is different than static. I mean, you could do something like that with a static, but it wouldn't be stored at the factory, so to speak, unless you have the static qualifier on it. Yep, absolutely. Yeah. So a little bit strange. And this part right here can be easy to forget, right? You get some really weird compiler errors if you don't do it. And you can't just say equals. This drives people bananas. It's like, I just want to initialize it to 0 like we did in the function, right? But we can't actually do that with a class. We actually have to move this out and define it and initialize it down there, okay? So once we do that, then we can say, hey, what are you, right? Cout widget : count, right? And it should be 0, right? Because we just initialized it to that. Okay. So once we start creating widgets, then we see that number go up. Okay. And so if we were breaking this apart into a .h and a .cpp, we would put the initialization at the bottom in or somewhere in the .cpp file. Okay, so that would be the convention. It certainly is not allowed to be inside of here. So no matter how you do it, you can't put it inside of that section there. Okay. So that's kind of us getting started. So let's see if we can do this. Let's create a box class and then give it a static member to calculate or keep track of its population. Okay, and we'll initialize that thing outside of the class. Okay, and then we'll increment it inside of the constructor every time something is called. And we can also use that like an ID value, a unique identifier. Now our boxes can have some kind of unique identifier based on when they were created. Okay, so let's take a look at this real quick. So here is our box, right? So let's create something called count. So it's going to be static int count, okay, like so. And you can see here we've got our constructor. So we're going to say count plus plus to increment the population. Okay. And I guess I don't have an ID on this one, but we could add one if we wanted to. But all the other usual things we might want to do with a box are here. And notice I just moved my private section to the bottom. So just something different, right? This is the public section. This is the private section. There's no restriction that you have to put that stuff up top. Okay, but now let's initialize our count, right? So int widget count equals 0. Did I spell that right? Widget? I think we got that. Box, sorry, box, not widget. Box is the class name, right? So, okay. So that's initializing it. And now we should be able to see how many total boxes are created every time by just saying box : count. Okay. So after we do this, we should have a count of 3. Okay. There we go. Okay. Okay. And you can add, of course, as many of these static things as you want in there. So the question becomes, oh, what kind of information do I want to keep at the factory? You know, what's useful for having a record? So if you think of our shared pointers, that we're just working on, how do they collaborate with each other so that they know that there are multiple shared pointers managing the same piece of memory? Very likely they have some static data structures keeping track of who's watching what address in memory. Maybe it's a key value pair map that's static at the class level or at the factory level, or something like that. But it opens up a lot of possibilities to do bookkeeping silently behind the scenes that enables things like those shared pointers, which are pretty cool. Okay, so there's our kind of stuff. And note again, you could have said check the factory, or I could have said my box.object count. And although that's confusing, it would have given you the number of the count at the factory. Okay, so we're just sort of reaching through the instance to find the exact same thing. In fact, let's just do that real quick, right? So if I just say I have box 3 here, if I just say what is box3.count, right? Box 3, which is an instance, 3.count. Okay, I should get the same answer. Okay, 3. Okay, which is confusing because it's like, wait, do you have an ID name box? No, or a member name box? No, you don't, right? It's in the factory. Okay, so if we can do it with these individual data members, we can also do it with our member functions. But what does that really mean to have a member function that lives at the factory? Okay, so it's kind of just that. And it highlights something that we might not have realized, which is that all of our methods so far have been going in the instances. So if an instance is like a box of stuff, it's not only including the data members, but it was previously always including all of our methods as well. So every instance had a copy of every method all the time, which might seem kind of wasteful. So if we just need a little worker function to do some math for us, why not store the method for that at the factory and just call the factory and ask it to do something for us, okay? Now, the only downside is that the methods that live at the factory can't look inside any instances, okay? So they can only work with what we give them through their arguments. But that could still be a really useful way to organize our methods, okay? So, and we can access them the same way that we access our data members, okay? So this will be a little clearer when we sort of look at some actual code here. But this would be my way of calling a method from the factory. My class, scope resolution, static method, parentheses, whatever that thing might be, okay? But we can similarly do it through a class instance. So there's an instance also reaching back and grabbing that static method at the factory, okay? The key thing to remember is there should be no utilization of the word this inside of this, because this refers to this current instance and these are static methods. So those are little surprises that come along from time to time. We're like, hey, why can't I use this? Well, we're at the factory. We're not inside of any particular instance, okay? And there's just a few other little things I just threw in here. There's no such thing as a const static method, right? So we can't really do this, right? That's not going to really do anything for us, right? So that's just kind of a weird animal that doesn't exist. And this over here is just declaring that the return value is const static, which really doesn't do anything useful for us either, okay? So really, there's really no reason for doing any const static methods, okay? So here's an example. Like, let's say instead of just reaching in and grabbing this count, we had a getter, right? Print whatever the count is, okay? Or print out the total cost of everything we produced at the factory today, right? So that print method could access a variety of pieces of information stored at the factory, okay? So we create these instances of widgets, right? We have an ID. We can increment the count manually that way if we want, or we could do it through the constructor, right? And then I can print the count at the factory, okay? There's no method in our widget that prints the count, right? It's only at the factory. We can use the instance to get there, or we can do the more typical thing and just say widget : print count. It's like going to the factory and saying, what did you produce today? Okay. Okay. So let's try this. Let's add a print count to our box class real quick, just so we can see it working. Okay, whoops, went too far. Okay. So here's our static object count at the factory, our constructor, incrementing the count at the factory. So let's add our method to print out the count. So we'll just say static void print count. Okay. Okay. Like so. Oops. And we'll just say cout. And we don't need to preface it with the class name. We can just say count, right? Okay. So we're inside of the class already, although I'm 90% sure about that, but we'll try that out in just a second, right? So that should get, oh, object count. That's what I need, object count. Okay. See if I'm right about that. Let's see if that compiles, first of all. Okay, there we go. Okay. So now let's call the static method from the class. So we'll just say box print count. Okay. Call in the factory. Okay. Okay. Three things created, right? Or we can use the instance again, which is a little silly, 3.print count. Right? But if you didn't know what that was, you'd be like, what is that 3 anyway, right? But they're really the same thing, okay? Okay, so that is a method that lives at the factory, okay? And we're going to look at a couple examples where we might use this. But again, for folks who might have looked at, big libraries, I remember the first time I kept seeing methods being called to calculate the square root of something, or not square root, but like the magnitude of a vector, or maybe to rotate something like linear algebra kind of matrix rotation. All of these typical things that we might think of as functions can be gathered inside of a math factory. So sometimes these classes are just used as collection points for related functions that really don't have anything to do with a particular instance. They're just a nice place to gather together a whole bunch of related math functions. So you might have somebody develop a class that does all of your linear algebra for you, right? And so it has a lot of functions that are really just static functions in the class. And maybe there's also some instances that get created by the class, but it's not always the case that we would use a class to just create instances, right? So we could have a lot of functions at the factory just doing nice, helpful things related to math, right? So here we just have a simple getter getting the count, but that could be so much more involved, okay? In our lab today, we'll do a little bit of a math at the factory kind of thing, okay? That's what we saw last time. Okay. Any questions on that before I move on? Okay. So const member functions. So this is just a little review. So sorry for all the const review. I know this stuff's pretty dry, but just remember const functions cannot make changes, right? So inside of a class, the member function or method is only allowed to change things that are allowed to be changed. That would include mutable, right? And it turns out that it also involves statics. So const member functions or const methods are allowed to change static values at the factory, okay? So here's just kind of a little demonstration of that. There is a static value at the factory, right? The mutable value is in the instance. It's not obvious at all unless you know what static is doing. And here is just a normal set function that's constant. So this would be an error, right? So our normal value here is not constant. It's not mutable. It's not static, but we're inside of a constant method. So we're not allowed to do that. Okay, which most of us might remember. This is okay. We're just learning right now that any method that is constant can change a static variable at the factory. That's allowed. There's probably good reasons for that. I'm not sure I know all the good reasons, but it's just something we can do. And then as we've seen before, a const can also change a mutable value, okay? And then here's our const method. That totally is okay to read something. It just can't write something. Can't change a normal variable. Okay. So couple reminders for you. Okay. And then the one other strange animal is called a static const data member. Okay. So back to the data members briefly. When it's static const, we can initialize it in line. And this is a little bit like that const expr that we were talking about a few moments ago. But it's basically just saying, hey, I don't want it to ever go away and I don't want it to ever change, okay? Which is a little bit of an unusual animal, but we can do it kind of like that, okay? Const static int class wide pi. It's like, this is the pi that everybody who uses the foo class is going to be using, right? So we can put constants in our class and initialize them right there if we want to, okay? And then we can access them like that. We can reach in the class and say, what is your constant value? And this is never stored in the instance, right? So many of you think, well, why won't we just call it a const? Well, then it's going to be stored in every instance instead of just at the factory, okay? Okay, so a lot of details to remember, I know, a little bit dry, but those are kind of the rules. So let's take a look at a student class. So let's try to develop something a little bit smarter, the way maybe we could assign Moodle numbers to ourselves when we all get our accounts at College Marin. So First off, let's figure out what's the largest ID that we would ever actually want to have a student ID be, right? So that should be something that the student class or the factory manages itself. It's like, hey, this is the maximum. You should never go beyond that, okay? And then also we'll keep track of how many students have been created, College of Marin, right? Students and professors, actually. And then let's also keep track of the IDs, okay? So we're going to keep a bunch of IDs in a set, right? So remember, sets are a lot like maps. They, by default, have unique keys. And we'll assign the IDs to students randomly so that no one can hack your ID. Like if I know my ID, I could jump one up the list and maybe I could find your ID. But when they're assigned randomly, it's a little harder to hack into somebody's ID, okay? So that's what we're going to try to put together. And yes, there's a possibility that we're going to have two students with the same ID. We're not going to try to fix that in this practice because we just want to keep things relatively simple, but it's a very fixable problem, okay? So let's take a look at how that's going to look. The factory is going to have the maximum ID and a set with all of our student IDs that we've created so far and a total count of how many students. And the truth is you could use the dot size method on your set if you really wanted to, instead of having the count, but we're going to kind of do both of those things. And there's reasons why that it's probably good to have some redundancy here, okay? But those are our statics. So we're going to be able to create a student with an ID that's assigned randomly, and then we will store that ID at the factory, and then we'll increment the count at the factory, okay? Like so, okay? And there. So let's do this one together. Okay, so here's the idea. We're going to assign a random ID between 0 and max ID, roughly. Okay, and then we'll increment our count. Okay, and we'll put that ID in the factory storage. Okay, so we should see something like this: created student 0 with some random ID, random ID, random ID, and eventually we're going to get a collision. So we're just using a small maximum number to help us test our, our error logic in our class there, okay? So let's go jump into this real quick. See if we can knock this one out. We'll maybe get you guys wrapped up a little early today, okay? So let's add our data members to our class. So we've got max ID. We want this to be static, okay? Okay, we also want a static count. Okay, oops, I see. Okay, and then a static set. So that's kind of a mind-altering consideration. It's kind of a cool data structure at the factory, okay? Now, all these are going to need to be initialized down below. So let's come down to that and just take care of that right now. So we're going to roll up our class and go to the bottom of our class and try to take care of all of these things, okay? Max ID count and student IDs. So let's just steal that code, go down below, okay? And we need to initialize these things. So we don't want to have the word static in there. That is always the case, okay? But we do need to have our class name. So our class name is student, okay? So, oops, T. And this is the one where if you don't know or remember to do this, it will drive you crazy because it's a very unusual seeming thing to initialize. So the max ID of 10 up here can't be set in here. We got to set it down below, okay? So let's go finish that. 10 count, it starts out at 0. And this doesn't need to be anything else. That's the other strange one. There's not like I got to set that to something because it's just an empty set of integer IDs. But we still have to do it down here in order to initialize it. I'm pretty sure we do. So I'm just going to leave it there and we'll see what happens. Okay. And then we're just going to create a whole bunch of students. So let's just see what we get with this. There we go. Okay. Student ID 768, right? And eventually we get a collision. Okay. So we could go back and add methods to our class so we could print out all the IDs so far, right? I could do that. Or I could loop through and just, if this is public, oh, but it's private. Yeah, so I won't be able to access these things if they're not public. So I'd have to kind of add a method or make that particular thing public. Okay. But just another example of kind of how we might dress up our class to do more useful things. Okay. Questions on that one?
Is there a name for this area above Maine where you're doing the?
Not really. It's sort of the global area, but in the same way that let me scale this back a little bit. In the same way that we create functions up here, it's kind of in the global space. And in fact, it could be in a .h or a .cpp file as well. So for sure, in our lab today, we'll kind of do that. We will need to do this work in the .h and the .cpp files and not in our main.cpp file, especially for replit folks. For folks who are only using ProgramIZ online compiler, we won't have separate files. But yeah, normally this work would be done in the .h and .cpp file. And this work right here would go in the CPP file for sure, not the .h. So that would be the convention that we would follow. Okay. So, and then of course we'd have to have some includes up here or includes down here to pull that stuff in. Okay. Good question though. Thank you. So there's our kind of semi-smart factory and instances. Okay. And so we could have methods in both places. That was really the revelation for me. So think about creating a 300 million simulation of people in the United States of America. 300 million instances. Or what about cells, right? How about 1 billion cells? That's a lot of instances. So you start to want to kind of prune down how big your instances are, and you kind of go, huh, does every instance really need to have a print method? Does every instance really need to have what's my atomic weight method? Maybe, maybe those things could go in the factory so that your instances of your classes are a little lighter. Okay. So those are some of the considerations that might come up. Okay. So that's kind of our main thrust for today. I wanted to take just a few minutes and introduce chess, and maybe give you a little time to try some chess if you haven't played chess before. You'll need to know a little bit about chess to kind of get your way through this assignment. It's not a lot, but if you don't know about chess, you'll probably end up learning it eventually. So it's not a bad idea to enjoy it now while you're not necessarily writing code, but let's just sort of orient ourselves to the game. So this is a great place to go. And usually students end up, if you don't already play chess over here, it's a really easy and funny place to go play. They did a great job. The AI is got some good taunts. And so it's a very easy and cheap and free place without needing to log in to go play some chess. If you want to read about chess, there's a lot of helpful information on this chess.com website, but this Chess Delights is really helpful when you start coding up your logic for your chess pieces. So you might want to come back to this slide a bit later on. But unfortunately, since we are working in a non-graphic area, we have to sort of come up with a way to draw our chessboard. So I have, for better or worse, named our pieces R1B for Rook 1 and Rook 2 on the black team. Okay, so R1B, R2B are our rooks. Horse H1B, horse H2B is really the knight, but I didn't want to use K twice because obviously we have a K down here for king. So these are our kind of rook positions. These are our knight positions. These are our bishop positions, and our king and our queen. Okay, black team, white team. Okay. So when you log on to chess.com, this is the orientation you're going to see. I think the white will always be at the top, I think. And I think or else it'll be random. It may switch from time to time. okay? So let's give this a try real quick. So just try to move a piece. So let's take a look at this. Oh, I didn't really want to do that. We got to do the reshare again. Sorry about that. Get me over here. Start again. Go all the way to the bottom. Start and share this. And I need this too. Okay, there we go. All right. So let's try this. Click in over here. So I'm just going to move some pieces, right? So I'm the white team here. So I'm going to move myself here, right? And the dodo is pretty fun to listen to. But that's our pawn. Our pawn can move either one or two moves on its opening move, okay? And it only can move in the forward direction unless it's capturing, okay? So my only choice is always forward unless I'm going to capture somebody, okay? So now its bishop is attacking me. I'm going to just see if I can, oh, am I in check? I guess I may be in check. And is that possibly checkmate? Did I just lose the game? Oh, thank you. Oh, right. Thank you. It's been a while. Thank you. Okay. All right. Queen's out. So I'm just trying to move a few pieces here. So the rook can move horizontally, right? Or vertically. Okay. Like so. Oh, I'm in check from the queen. All right. This is going to be embarrassing for me because I have not played chess in a while. Okay. Here comes the queen. So anyway, worth just warming up your piece move skills there. And it's free to play. You don't need to log in. Now, in terms of how we're going to represent this in code, so that's kind of my goal for opening this up. Notice that we have rows numbered 1 through 8, where the nearest row is down below and 8 is up above. So these are standard chess moves. So we're going to adopt this convention. And we have letters A through H on the columns. So if I want to move a piece to a particular location, we're just going to specify the row column like we always do. And we'll do it in the way that, most chessboards are laid out. Okay. So that is kind of our first thing. Okay. So keep in mind these different kinds of moves. Also keep in mind that in terms of a position, the white pawns are going to move in the plus or row plus plus direction. Okay. So I know it's a little confusing because we've all kind of gotten used to counting rows in the downward direction. We'll see this here in a second. So that's a row plus plus. Okay. That is a row minus minus. Okay, so this is definitely going to come to play in your code logic when you're kind of eventually doing this, okay? And this is kind of what our board is going to look like. You don't have to write, the vast majority of chess has already been written. You're going to be putting the logic in the individual pieces for the most part. So it's not a lot of code. It's actually surprisingly little code. Okay, but the logic and what we're going to be doing with inheritance is a little confusing. Okay, but this is what our board is going to look like. Okay, and we're going to just say, P1W move to 4A, right? And if that's a legal move, then it should move. But if I say P1W move to 4H, your logic should say, sorry, that's not legal. I can't move there. Okay. So there will be lots of little bits of layered logic we'll slowly bring into this. But obviously knowing how our different pieces move will help you get started on that, okay? So let's look at our chessboard.h so we can start to get ourselves familiar with the data structure we got to deal with here. So chessboard is an interesting decision because we do not have an actual two-dimensional data structure. All we have, aside from some constant values, is an array like our puzzle pieces, but they're actually the pieces that are going to be on the board. So there's 32 of them, okay? And the individual pieces know where they are on the board. So there is no actual two-dimensional array. We have to go look at the individual pieces to see where they are in the game, okay? And additionally, this piece class is what we will come to know as our base class. So we haven't talked about inheritance yet, but obviously we need a chess class and we need a queen class and we need a bishop class, but they're going to derive from the parent class or the base class, which is called piece, okay? So our pointers we get to have as being generic pointers to the base class. But here we will see here in the next couple lectures, we can fill up that array with pointers to any child class that inherits from the piece class. So this is one of the examples we refer to when we talk about polymorphism. Okay, so we'll get into all of this. So I just want to explain a little bit about what that is. We'll keep track of whose turn it is. Is it white's turn or not white's turn? Okay, so we'll use some Booleans there to simplify that. Okay. And notice I created a constant for white or black here to just make your code a little bit more intuitive. So sometimes it's hard to remember whether we're representing white as true or black as true. So we'll just use symbols for that when we're doing our logic, okay? And we'll use the convention that white goes first. That's the convention for the different teams, okay? So this is the big piece of our chessboard. Obviously, we're going to have to allocate and hook pointers up to our chess pieces here. And you'll be maybe relieved to know that we are not going to use shared pointers for chess. Everybody will be somewhat tired of that by now. But let's take a quick look at Program IZ Pro, or you can click into Replit if you like. And hopefully I'm all logged in here. So there are a lot of, oh, I thought I was logged in. All right, let's see if I can actually do this without fail. You. Okay. Sign up. Oh no, I need to sign in. Sign in. Okay. Yates at .edu. Okay. All right. What am I missing here? JD Yates at .edu. Total concentration. I get it. Great. Okay. So you'll notice we have an awful lot of data H files. So queen, king, rook, one for every piece. You'll need to create a CPP file for each one of these, not for the piece.cpp or the piece.h, but for all of the pieces that play in the game, okay? And so if we go to our chessboard over here, you can see there are a lot of methods, but fortunately, most of these have been written for you, okay? So again, you're really only going to be focusing on the logic that goes with a particular piece. So let's take a look at our pawn, for example. Our pawn constructs at a particular row and column. Here, I'll make this a little bit bigger for you. We won't get into this too deep, but I just want to kind of demystify it a little bit for you. So is it a white pawn or black pawn? And what is its screen name? Okay. So you're going to need to write the code for the equivalent CPP out of class for this thing. Okay. Same for all of the other pieces. So it's not a ton of code. It just is maybe a little confusing. Okay. And we'll take you through all that. So most of this stuff is already written. You don't have to worry too much about writing all this stuff, right? So is occupied, is clear, take turn. All of these methods are crucial. We'll go through them all one by one, but the comments are pretty dense to help you know if you want to jump in early. Okay, is the king in check? That's a pretty tough one. I wrote that for you. And if you want to do the bonus, you can do is checkmate and is stalemate. These are challenging bonus questions, but they're there for you to do if you want to do them. They're not required for the actual assignment, okay? So we'll slowly work our way through all this stuff, but when you see to do in any of the .h files, that's a clue that you need to implement that particular thing, okay? And these are the bonus, right? Those are bonus, so can be skipped, okay? Okay, so let's just see what happens when we construct. So the constructor is written for you, right? So we're going to just go ahead and create a dynamic allocation of a rook. You're going to write the constructor for the rook, but this is how I'm going to hook it up once you write it. So it's like we're all on the same team together. I'm kind of architecting and you guys are implementing the pieces in the game, okay? So I'm going to hook them all up. So I hang on to their pointers. I'm going to increment a counter so I keep track of that stuff as I add it. I'll do the black pieces, front row, back row, white pieces, etc. Right? So all of those things are going to be there. And then crucially, many people will forget this, each piece is going to have a pointer back to the board. So this is the board and pieces P is the piece, has a board pointer inside of it, okay? So this stuff is all written and is working, right? So here's how all of our pieces obviously lay out. Kind of matches what we said before, okay? So again, notice there's no two-dimensional array here. There's just a one-dimensional array of pieces, okay? And so if I want to know if a particular location is occupied or not, I simply have to do a linear search. It's not super sophisticated, but we only have 32 places. So that's not a slow thing. So I'm going to go through every place and I'm going to ask, is that particular piece captured? If it's captured, then it's not in the game. So I can just sort of skip to the next loop, okay? So I'm going to look through every particular position or every piece I have and see if there's anything at that location. So if I find a piece that's row matches the row or column that I'm looking for, then I would return that that thing is occupied, okay? Return true, okay? Otherwise, if I don't find anything, I return false, okay? But this one is written too, but it just sort of gets you in the thinking of how our data structure is laid out, okay, and how we're going to access those pieces, okay? So that's what we're doing every time, right? So you're going to be given a README, the main, the piece.cpp, and the piece.h are fully written. These are the base class that allow you to build your pieces with this feature already built in. There's a very large test me that's quite sophisticated. We'll all get better and better at how to use it. And then there's input data for famous games, Bobby Fischer games, etc. Famous games, famous moves, fastest stalemate, fastest checkmates. There's probably about 15, 20 games in there that we will test, right? And so your board should match the actual famous game at the end of the game after 20, 30 moves, okay? So that's probably the hardest part about this is getting everything exactly right so you get the exact results. So these are given to you as well. So you're just going to really be writing 1, 2, 3, 4, 5, 6 .cpp files. And the good news is that with inheritance, you will be inheriting all of the logic of the base class. So you won't really have to write a lot of code. Okay. So it's really more of a logic challenge than a coding challenge for this one. Okay. So this is what we mean by inheritance. The king inherits from the piece. The bishop inherits, the knight inherits, the rook inherits. But we will also explore this kind of inheritance on the bottom. The queen moves kind of like the bishop and like the rook. So the queen is going to inherit from these two because she will inherit their unique moves and combine them together. So that's an example of what we call the diamond problem or dual inheritance. So we will study that aspect of class inheritance as well, okay? So, but again, these are 3, 4, 5 lines of code. Maybe some of them are 15, 20, but at the most, or at the least, one of them is like 1 line of code. So it can be pretty simple to do, okay? So that's a look out. 2 weeks ahead, we will talk about inheritance. For the moment, we're just sort of going to exercise our static new understanding with our lab. So let me flash this one at you real quick and let you guys get on with it. So all we want to do is finish implementation of the vertex class according to its .h file. So if we see statics in the .h, we need to do the correct thing in our .cpp file, okay? So I'll show you this in the Program.iz version. But essentially, when we run our program, we should see this output, okay? Created a vertex, created a vertex, created a vertex. Just so happens this vertex is going to be V0, V1, VLERP, and I'll tell you what a LERP is here in just a second, okay? But we'll use statics to keep track of all the things that have been created, and we're going to create a static method called LERP, and I'll tell you what a LERP is here in just a second. So then we'll get you guys out of here, okay? So that's what we want to do. Okay, so let's take a look at what our vertex is. It's got an X and a Y coordinate. It's got a static population. So that's at the factory. Okay, so that's what we've been doing all day. Here's our constructor, right? So that's the prototype for the constructor. You've got to write that out of class. Okay, that's pretty straightforward, right? You're just initializing these things based on these. And then we're going to write this funky static method called LERP. LERP stands for linear interpolation. So I'm going to give you all the math, but if I have 2 points in space and I want to find a third point that is 3/4 of the way through them, I do a LERP. I get the first vertex, the second vertex, and the percentage of the way from 0 to 1.0 that I want to go. So this would be 0.75%. So this is how we find a new point in space between in a 2D space or even in a 3D space, okay? So that's an example of a mathematical function that we might as well keep at the factory. It's got some, fun little math in it, but it doesn't need to be copied into every vertex. Why kind of fill up our vertex with that, okay? So somebody gives us the A and the B, and then we just return a new vertex, okay? So that's what we're going to write as well. Okay, so the math for this is not intimidating. The X for our new vertex is the X for the A plus the BX minus the AX times T. Same thing for the Y coordinate. Okay, so nice little orthogonal, math in the XY plane. So that's going to give us our new vertex that we return, right? So we're going to have to remember how we do that in C++. But your LERP between vertex 0, 0 and vertex 10, 10 at 0.5 should take you 5, 5 along that line, okay? So that's one way of testing that, okay? And then a print me, right? A static print me that's going to print out some description of any particular vertex, right? So we'll have 2 static methods and a static population, and that should get you out the door, okay? So quick peek at the code, and then I'll let you guys go. So if you're using Program IZ online, I have done you a favor and broken up the .h. So here's the .h, and you have to write the .cpp right there, okay? And then here's some instructions for creating and lerping down there. Okay? Right, so I leave you with that. For the rest of you, write a CPP for that. If you want to create the vertex CPP. Okay. Thank you. Give you the rest of the time back. You can work on your homework. Otherwise, see you on Thursday. Thanks.